Okay, so good afternoon, everybody. My name is Sumit Puri, CEO and co-founder here at Liqid. Excited to give you guys a quick update on how we view AI workloads and how we view them being serviced on on-prem infrastructure. So I'll move quick. If there's any questions, please chime in and ask. So the first thing that we like to think about AI, and AI is not necessarily an event. We think about AI as a workflow. Different phases of the AI workflow actually require different hardware resources. If we think about data ingest, that's a networking intensive activity. If we think about data tagging, cleaning, scrubbing, that's normally a compute intensive activity. As we go on to data training, we're usually using the big GPUs, the A100s, the V100s, 2 of them, 4 of them, 8 of them, sometimes 16 of them inside of a single server to reduce our training times. And then we move on to data inference, which is yet a completely different hardware profile. And many times you have very large data sets sitting at the center of this whole thing. And we're trying to shuffle data between different physical machines. We kind of take a different approach of this and we say, let's take a look at a composable AI platform where data sits at the center of the universe. So here's an example of the kinds of solutions that we are building based upon disaggregated infrastructure, specifically targeting AI-centric workflows. So in this example, we have 4 compute nodes, but instead of putting the GPUs, the storage, the networking cards directly into the compute nodes, we put them into an expansion pool. So when compute number 1 needs to do his data ingest thing, let's give him some NICs. When compute number 3 needs to do his data training thing, let's carve out 4 of the $10,000 V100 GPUs and give it to that compute. And then when he's done with them, let's free those resources back out into the free pool and let somebody have at my very expensive hardware, right? And so by fundamentally disaggregating the hardware and then pulling in the appropriate hardware for the phase of the AI workflow that you're at, we think this is how you get much better utilization out of the hardware that you're deploying inside the data center. And it also addresses that data gravity problem, right? Think about it. You know, many times you're copying a petabyte or hundreds of terabytes of data across a low latency network connection. In our world, we can actually just pick that storage profile up and move that storage to the compute that needs it. So this is the kind of approach that we are taking when we talk about disaggregated infrastructure specifically for AI workloads. It's not about monolithic converged machines with a fixed amount of compute GPU ratio. It's about the ability to dynamically change these ratios depending on what phase of the AI workflow that we're actually at. Moving on, let me show you, because I know there was a question earlier about the physical layer. Let me show you how at the PCIe physical layer, we actually interconnect all these pools. We are a multi-fabric solution, so in the sense we can do this across other interfaces beyond PCIe, but when we're talking about AI-centric workloads, it just so happens PCIe is that ideal connection to go build big, high-performance systems around. So the first thing that we do is we take a PCIe adapter card and we plug it to the PCIe socket of the server, and that provides us into the connectivity into our PCIe fabric switch. The GPUs, the storage devices, the networking cards, the FPGAs, whatever the peripherals are, we don't plug them directly into the server. We plug them into an expansion tray. So this is what a disaggregated rack of infrastructure actually looks like. These are our compute nodes. They can be any compute node you want, a 1U server, a 2U server, a 2U4 node. It doesn't really make a difference to us. We are compute node agnostic. It could be a single proc, a dual proc, a quad proc. It doesn't make a difference. And then we have our trays of resources. This tray over here holds our accelerators. This is a 4RU chassis that holds up to 10 accelerators, and we can have multiples of these chassis on the fabric. And then we have our tray for Offtime Memory, and then we have our tray for NVMe storage. And then we come in with the Liqid software, and we carve out resources, and we dynamically assign them to hosts.
Hey, Sumit,
Yes,
is the Offtime Memory, is that storage class memory? Is that NVMe storage SSDs, or is that, you know, DMEM kinds of things?
Yes, it's not DRAM. So right now, the way that we handle disaggregated memory is we disaggregate Optane NVMe devices, and then we're able to work with Intel and the IMDT drivers and turn that Optane memory into emulated DRAM. So until we get to, yes, sir.
Whoa, when did that come about? That's got to be fairly new.
No, Intel's had IMDT drivers out for a while. We're just able to now leverage those drivers in a disaggregated composable architecture.
So you can disaggregate the memory?
We can disaggregate Optane memory in a standalone pool connected over PCIe Gen 4 to these servers, and then turn on the IMDT drivers and treat that Optane
As
storage
DRAM.
as DRAM.
Oh, thank you.
No, you're welcome.
Do you have any metrics on the latency on that?
Yeah, the latency through our fabric is the latency of PCIe. So at PCIe Gen 4, we're 80 nanoseconds through the fabric each hop.
Outstanding.
Yeah. So this is what, what we say, like the elementary view of disaggregation looks like, right? You can take as many GPUs, as many storage devices, as much Optane memory, compose it over to that host. And as far as the application layer on that host is concerned, all of those are locally connected devices on his motherboard. The host, the application layer, the AI algorithm will not be able to tell that those GPUs are physically sitting in a separate expansion tray, or the storage is an expansion tray. And it's dynamic in the sense that when my application needs another GPU, we don't send a human with a screwdriver to the data center with a cart and power down servers. We simply reprogram that fabric layer and hot add or hot remove devices from running servers. So this is what we refer to as the elementary view of what disaggregation looks like. But the way that we're doing this is at the rack scale, right? So when we start looking at big, large, scaled out environments using disaggregation over PCIe, this is a representative example of what it feels, right? So in this example, this is a 3-rack composable pod. We have roughly 100 compute nodes. You have a large pool of storage class memory, a giant pool of traditional NVMe storage, and over 100 accelerators. And in this example, we can turn any one of these compute nodes into a high memory node. We can turn any one of these compute nodes into a GPU node. We can turn any one of these compute nodes into a high memory, into a high storage node, right? And so the idea is, let's not a priori ahead of time decide how many devices we're going to put inside of each compute node. Let's deploy them as fluid resource pools and then compose the server based upon what the application layer is requiring.
So 1.1 petabytes is not that much storage.
We can turn the knobs as we wish, right? This is just an example. So if we needed to build a system with 27 petabytes of storage, like we did for the Department of Defense, no problem. We can do that also.
Can I connect external storage that I already have?
Yes, you can. We can help you guys integrate external storage into a composable environment. Right. So if you have existing Ethernet-based composability, we can add that into a PCIe composed architecture.
Nice. I like it.
Can a composed server contain more CPU cores than exist in one compute node? For example, can I build a host with 2,000 CPUs?
You cannot. No. So today the unit of composability is the server, right? So we can add and remove things from the server, but we don't take two servers and magically munge them together to create a big giant. There's people out there in the industry that are writing software to be able to go off and do that. That's not the focus of what we do. You have to think about the Liqid solution as a physical layer hypervisor. That's what we do, right? Just like VMware slices and dices inside of a virtualized environment, we are slicing and dicing at the physical layer. So that's the way to think about our solution. And, just like Josiah said, he's working with some super important large customers who want to compose a system to a single server that have 16 GPUs, 16 Mellanox NICs, and a whole bunch of storage connected directly at the bare metal to a single compute. Now nobody bends sheet metal like that. Why would you, right? Power, heat, PCIe lanes, all of that kind of stuff. But in a disaggregated composable world, we can compose and create any ratio that we need here. Right?
Is an acceptable analogy that what VMware does for an operating system, you're doing for AI?
AI is the first primary workload, but I would kind of extend that a little bit further, that this is for infrastructure. We are slicing and dicing infrastructure at the bare metal. AI happens to be the first application that we're successful with, but this can benefit in edge environments. It can benefit in traditional HPC. It can benefit in enterprise cloud, right? To us, just like VMware plays in a whole bunch of other environments, we think our technology actually permeates beyond just AI environments. It just so happens when you can do things like PCIe peer-to-peer amongst these GPUs, as Josiah was describing before, This is how we unleash the next level of performance in the data center. Let all of these devices, the storage, the GPU, the NIC, all of these devices communicate directly with each other without having to do multiple memory copies in the x86 processor. And so this architecture around peer-to-peer RDMA, this is what matters. This is how we get to that next generation of data center architecture. So beyond just the flexibility portion that disaggregation brings, there's a whole bunch of performance benefits that are unleashed when you disaggregate over PCIe and then recompose over the native interconnect of the device. Today, it's a data center first, right? Everything for the first time is speaking a common language, which is PCIe.
So are you using this peer-to-peer memcopy PCIe Linux solution that's been available for a couple of years now? Is that?
No, that's just as Josiah said, right? This is kind of our secret sauce, right? This is what we enable at our fabric layer, is the ability for these devices to speak directly to each other across large, disaggregated, scaled out fabrics. Today, a lot of GPU to GPU, but soon NIC to GPU, and then NIC to storage, and then NVIDIA is inventing GPU to SSD. So inevitably, all the devices will be communicating over this RDMA data.
Are you adding software to the operating systems at the host level, or is it all outbound?
It's all at the fabric layer, because as we mentioned, for the first time, everything is speaking the common inbox driver, which is PCIe.
I got it. Thanks.
You got it.
Since you're using PCIe, can you still take advantage of NVLink for the GPU cards to exchange data between cards on the same board?
Yeah, so if you have a system that has NVLink, absolutely, we can allow that NVLink transaction to continue on its own. And then what we do is we augment that NVLink capability with storage and networking capability on top of it, right? So we can also look into things like breaking up NVLink type architectures also.
Yeah, I do have another question. A lot of the AI pipelines, as you know, they use CPUs, FPGAs, and GPUs. How fast is it to compose and decompose? Meaning, if I have to run an AI job and I have to use all these resources for the next 5-6 hours, do I all pre-compose them, or do I just compose and decompose as I go along?
So the decomposition or recomposition takes about, I'd say, a minute or two, depending on how many devices you have, because we do have to basically rebuild the PCIe, kind of that logical layer, and unmap the devices from the host and make sure there's nothing going on and all that stuff, so don't pull a device out that's active. But yeah, it's about 1 to 2 minutes for. Actually, it's about 1 minute for let's say like a node that's got like 16 GPUs and 16 HCAs, or 32 GPUs. So.
And then you have to boot the server with a new configuration?
No. So we have a hot plug enabled for our devices. So you just remove it, and that's really where today we're not trying to become the orchestrator, because there's already really good tools out there, and that's where Slurm or Kubernetes would come in. And when you need to spin up a new node or change your workload profile, or like with Slurm, it's actually contained in the job description. I need these many GPUs, and actually HPC, I would say, is where we see the most of that highly dynamic changing, because they're one day they're doing FPGAs to do some special particle simulation or something, and then they're doing AI that evening. There's some big AI job, so they probably do the most dynamic recomposition out of any of the.
Do you see any of your customers using Kubernetes and stuff in a hybrid situation with Liqid and on kind of capabilities in the cloud?
Yeah. Oh, absolutely. Yeah. So our Kubernetes integration supports. We just fit into Kubernetes, into the Kubernetes ecosystem. So as you spin up your containers, if they have a resource profile, that's you need to do on-prem, you do it there. At the same time, you can just use Kubernetes to scale, out into the cloud if you need to. We're just kind of off to the side. So we don't get in the way of any of that stuff. It's just kind of an added capability to your existing tools.
How about multi-tenancy? How do you deal with groups that run multiple or want to compose hardware? How do you prevent one from running over the other one? Is like reservation. I mean, it sounds like you're building a mini public cloud, right? Where you kind of allocate resources.
Yeah. So the way we do that is, again, we integrate with the existing job schedulers and resource schedulers that are out there that kind of handle the really they traditionally handle the software, the scheduling of the software on an existing hardware resource. And all we do is there's an additional API in our Slurm API, for instance, that just allows you to specify what devices that system needs. So that's kind of the gatekeeper, whatever your current orchestration tool is. There's kind of three ways to compose the device or recompose the system. So go ahead.
Yeah, go ahead. Sorry.
Yes, there's three ways to get in. One is directly through the management interface. So think the management interface to your 200 gig switch. Same kind of concept. A sysadmin has access if he wants to cut off a link and terminate communication between two nodes in your infrastructure. He can do that, but that's like admins are the only people that have access to that. But a lot of lab testing and stuff like that. People use that often. And then the second way is interfacing with our API directly. So if you actually want to, you have a very specific use case. For some reason, you're not using Slurm or Kubernetes. We see this sometimes in the HPC space with kind of weird, I guess, kind of odd edge cases where they'll actually just integrate with our REST API and just tell the system, they'll have an application that they write that controls the composition and decomposition. And then the third way is with the job schedulers that are out there, Kubernetes. So right now we have Kubernetes, Slurm, and Redfish, and then I'm actually working on an Ansible integration. But those are all basically admin level, root level tools where those tools are responsible for resource assignment. So we leverage those. Those are the gatekeepers to prevent someone from stepping on somebody else's device while they're using it.
Right. I mean, it can be challenging, right? Because people can add and remove GPUs and servers and Slurm. Slurm kind of has to know what's available in in some real-time fashion, right?
Right.
So.
Yeah. So there's a manifest. We do provide Slurm. So Slurm can interface with so there's the fabric itself that everything's connected to. So there's a manifest of all the devices and how they're interconnected. And then Slurm uses that to make decisions about job scheduling and all that. So traditionally, you don't actually have people plugging, although you could do it. I probably wouldn't necessarily, I'd have to think of a good reason to do it, where you're actually installing, new enclosures with GPUs into a cluster, or really into the same server that an active job is being run on, where you're, physically, adding resources to the system. But I think that's kind of the only thing, it just might have, I'd say just a good thing probably to plan ahead of time on that one.
Thank you. Maybe another question regarding the tool integration. I mean, maybe Terraform is maybe not the right tool for you guys, but do you integrate with tools like that could potentially help kind of code as infrastructure or infrastructure as code, I guess? Yeah.
So actually, so I'm working on that a lot in my lab. So most of what I do is engineering, stuff around the AI, workloads. And what I have personally found, so there's kind of two trains of thought in the company. One group of folks is like, hey, let's just put it all on the switch. Let's have the management switch. Let's have our management switch be that orchestrator for the hardware. And I think that's a great idea, but I also think that's like a 5 to 10 year project to do that, as well as Ansible and Terraform and Maz already do that. So although, we need to have the interfaces to those, those tools, what I actually am doing in my lab is using, so there's kind of, if you think of, if you kind of take a step back from Liqid and you look at your infrastructure as, okay, all of this is disaggregated. How could I control it all to do exactly what I want, when I want it to do it? What do I need to do? So you basically need something that does bare metal provisioning, something that does OS provisioning, application provisioning, and then, whatever else you want to put on top of that, whether it's Kubernetes or, VMware or whatever. You need to be able to control the PDUs, the full stack. And then add Liqid into the mix. Then you have to compose the system, the hardware resources. So we have that piece covered. So what I'm doing in my lab is I'm using Ansible. So I use Maz to do, so Ansible is my driver. So it's like my Terraform. So Ansible is my driver. It drives Maz and Liqid, the Liqid fabric, and then Kubernetes or whatever else I'm running on there that day handles the application level tasking and composition. And then I run Slurm as well in there, but I personally don't use it a ton for kind of what I do. But Ansible is the driver that hooks into everything and, controls the whole, I kind of have one touch point to control everything. So that's kind of how, that's how I do it. And you can do that today with Terraform due to our REST API. So that's what I'm interfacing with. It's just the REST API. We don't have an official Ansible or Terraform plugin yet, but it wouldn't be, we'll probably just reuse the one I'm working on once I kind of.
Right. I mean, I think that's what most people are looking for, is the ability to reproduce an environment, right, later on.
Yep.
Hey, Josh, is there a limit to the number of, and I'm not even sure what the right question is, number of nodes in your fabric? I mean, you showed like a 3-rack solution with, I don't know, 500 compute nodes, and I have no idea how many GPUs. I mean, there must be a limit. It's a physical number of nodes.
So really, so there's 2 limits so we used to have a limit of whatever the number of PCIe bus addresses were that were available on our server. So there's kind of like, I guess there's kind of 3, there's a couple nuances. So I'll try to cover them without confusing myself or you guys. So basically there's a node level limit. So a server from like Dell, for instance, like a Dell 7525. I use those all the time. I really like them because they're pretty beefy, and they get a ton of PCIe slots coming off the back of them. Well, each server has a certain number of PCIe addresses. Usually that's 256. So if you have a server that already has a ton of peripheral devices, that's going to eat into the PCIe addresses, and that will limit the number of devices you can connect to that specific server. So it's all based on, what that node is capable of fundamentally seeing from a PCIe perspective. Then you also have that same limit applied to a single management switch. So our network switch, just like, kind of regular switches, they have a certain port limit. Our individual network switch has a port limit fundamentally, which is still based on that PCIe address space. So it's about 256 devices today. And then after that, you cut out there. You might be on mute, Ray.
I'm sorry. Now, would a box of GPUs be a single device or one device per each GPU on that? It would be multiple devices.
It would be so usually we deploy, what we typically do is, and actually this is kind of due to the nature of the PCIe bus. So when you're deploying GPUs, there's at the core, not the core really, but our core building block on the PCIe bus is a PLX switch. So it's got 6, by 16 stations coming off of it, and that's your core building block. So when I'm doing like AI configs, if it is a individual node, I'm just going to fill up all those by 16 slots with as many GPUs as I can, and you'll have a 32 GPU server basically. If it's in a cluster environment, which is most of where the large organizations are going, they're building out their own training clusters and stuff like that. And definitely, the hypers, the Googles and Facebooks, they're all, just going crazy right now with this stuff. What I do in that case is I'll split HCA and GPU for the most part. It's kind of a one-to-one mapping. So like on one of those PLXs, I'll have for 2 GPUs and 2 Connect X6s. So that's kind of the pairing, because that really, both of basically the GPU and the Connect X6 bond together, and then they communicate out to the rest of the network during training or inferencing. Data's either coming in or going out, or going both ways. But that's the basic building block. And then what we do is we take that and we scale it up into an actual enclosure. Today we go, I think it's up to 10 GPUs in a single enclosure. And that's kind of like the base, 4U pod of GPUs, and then you just stack those to scale up. So there's a system I have right now, it's going out the door, that basically each node has 4 enclosures in it, 16 GPUs, 16 HCAs, and that's really like the node level thing. Or excuse me, the cluster. That's like the deep learning training cluster architecture, because you want to make sure you've got enough bandwidth for the nodes to talk to each other and the cluster. So that's kind of how I do that. And then from kind of a scaling everything beyond, we were talking about the limit, like how far can we scale? Well, there does become a point where, as you're connecting we can connect multiple management switches, just like a regular, Ethernet network or InfiniBand network, and start, stringing out the network to kind of build, this a very large pool of resources. But you will begin, depending on your workload, especially with AI, you'll end up starting to run into bottlenecks going between switches. So usually that's why
additional hop kind of thing with additional latency, et cetera, et cetera. I gotcha.
Yeah, and it's kind of like, it's really similar to NVLink. So the reason why NVLink only has six switches in there is they're out of ports. And that's basically a full crossbar, right, between all those switches. But then if you added, a bridge in there, well, that's a huge bottleneck. So,
and Josiah, that brings in my next question, which is, what are you doing? What's your process for preventing hotspots or bottlenecks in general in your fabric?
So the fabric, well, designing things. So when a customer has, typically there's a set of general use cases that are very compute intensive. And that's really where I would say you primarily would need to worry about it. And AI is kind of the big one, because you're pushing a ton of traffic across HCAs, Connect X6s basically over InfiniBand, and then you're bringing a bunch of data in over usually 100 or 200 gig. And then you're computing, there's a bunch of GPU to GPU communication that's going on. So that's probably our most complex workload we have to deal with. And kind of from there down, it becomes much easier, because the devices aren't really fully being utilized. You're recomposing for convenience or cost savings and stuff like that, versus pure, performance. So definitely, when we, send something out the door, we don't, we're not just like, oh yeah, it'll, buy these and it'll solve your problem. We definitely talk to, our customers and make sure we understand the use case, so they're getting a good configuration, because they have the ability to design a PCIe bus however they want. And in general, at small scales, it's, there's a large margin for error, but at large scales, you could run it, like if you build a cluster, for instance, in the core building block wasn't, or core architecture wasn't right, you could end up hurting yourself.
Who is the person driving the acquisition of Liqid inside teams? Is it the head of AI, head of IT, infrastructure? Who says when Liqid is worth buying?
I don't know. I build. I guess what I'm focused on doing is I come from the statistical learning world and was a ML guy by trade for a while. I guess I still am. I had an HPC background too. So my focus is getting the technology in the hands of the people that could kind of use it the most and making sure it works well for those use cases. So they're not just buying something to buy it.
So I have the opportunity to get in front of customers quite a bit. In fact, last week was my first business trip out to DC area. So I can tell you that it is a bit different than it was in traditional. I'm from the storage side of things, typically. That's where I grew up for the last 15, 20 years. And for this type of solution, we are talking to infrastructure folks. So, the managers, directors, et cetera, around the infrastructure side, but also people like Josiah, right? So the researchers, the AI folks, it's a bit different, right? So I would say it's a bit of both. And we also find that the AI people can be the decision makers in some instances as well, because it's their project.
Actually, George, maybe you know the answer to this. Given all the different types of workloads you do, you got the vSAN stuff, you've got other bare metal stuff you do. How much of your purchaser base would you say is AI as opposed to some other workload?
Yeah, I would say based on the work that Josiah's been doing, 24 hours a day, 7 days a week, maybe sometimes 8 days a week, I would say most of it is HPC and AI focused.
75%, 85%?
I would say probably 80%, 85%. I think that's where you're going to see it first. We're starting to have more conversations that are moving further down into kind of generalist areas, like in the data center infrastructure. We're getting ready to announce some new features around Vmware here shortly in the next month. That's going to open that up even wider. Josiah showed a slide at the very beginning that talked about a lot of the innovations that around infrastructure has been done at the software level for the last 20 years. I've been in IT. I was an IT manager for years before coming onto the dark side. And not much has changed from the way that we, build servers, build infrastructure. It's all the same. It's gotten faster and bigger, but we're still ordering it, deploying it, and scaling it the same way we did 25 years ago. So this is really providing a new mechanism, a new way, new lever for people. And what you're going to see is it's going to start here with these super smart guys like Josiah who are going to be buying this stuff, and then guys like me who are more the generalists are going to look and go, hey, what's that? I want that too. And then they're going to start pulling that into the data center more. So you'll start seeing more of that.
Yeah. And that's kind of what we're seeing with our OEM partners. We get brought in when they don't have the tool in the toolkit that a customer needs. And usually they're, large accounts that have, they don't want to lose. So they bring us in and, we solve the problem, and then it happens again, and then happens again, and then people start talking, oh, well, wait a second, why are we using this for VMware? Because the concept is sound. It's just, I think it's been proving it, proving in the field. And I think we got a little lucky because the AI space has been taking off so rapidly, where there is this huge demand for a specific sized server, especially with the large companies that have been doing this, have been doing, applying ML for, 10 years or so. They've kind of figured it out that, it's just this big numbers game, basically. So they've got, the requirements pretty dialed in, and, we can provide that today. And that's kind of the, attached to a Dell server. Yeah. Dell maintains the account, and the customer gets what they want. And
so do you guys work with? I think it's multi-instant GPUs, a MIG solution that NVIDIA so it can split up a single GPU across multiple compute tasks and things like that.
Yeah, yep. So MIG, basically anything above the PCIe bus we support. With MIG, the one question I do get is, hey, can I carve that up into 8 MIG instances and send it up to 8 different servers? And today you can't.
Yeah, it's got to be the same server.
Yeah, and that's just due to the driver interface. So MIG talks to the driver, and the driver talks up to the host. So that's where that limitation is, and it's possible to do that. It would be possible, if we collaborated with NVIDIA on that, because we have we're already doing that with devices, right? So we could,
So speaking of like namespaces and stuff like that on an NVMe drive, you could split that across multiple servers.
So a single NVMe drive or multiple?
Well, a single NVMe drive with multiple namespaces on it. Yeah.
So if it shows up so one of our earlier products was a PCIe NVMe drive. So it had several U.2s or M.2 drives on it, and we actually did it for that reason. People were like, "Well, hey, I want 32 terabytes, but I don't need it all the time. This is a scratch disk. I'd like to be able to carve it off and hand it off in chunks of 2 terabytes or 4 or whatever, based on the device level. So as long as it's on there's a PCIe switch in the mix between the individual namespaces, we can carve it up. So we carve it up by PCIe interface though still. So we're not splitting
right.
virtual file systems up and stuff like that or anything like that.
Right. Okay.
So,
thanks.
I got a curiosity question. I don't know if you would have an answer for this, but particularly places like finance companies, they obviously want to run the HPC and AI training model, everything in their private cloudish or private data center. But one of the things they're feeling a pinch is because how heavy and intensive this could get. They couldn't do the whole thing in the private cloud. So a lot of them are building an infrastructure in such a way that they do an overflow into the public cloud. Right. So while they do that, they also want to have a control of, which data they want to send it there,
right,
and also which computational processes they want to send there. So they want to have a mix of, I want to do these things in here in my location, and the rest of them I want to overflow to the cloud.
Right.
Do you have any customers who are trying to do that? And if you so, how do you solve it? How do you coexist with the public cloud while doing a model training or inference or a combination?
Yeah. So for training, you can still. So we don't get in the way of any of the frameworks that exist today for training or inferencing. So everything above the PCIe. There's no driver that goes on the server. We have the side channel controller that controls everything, but the host isn't aware of it. So the application isn't aware of it. So the way customers are doing that today is they're just, using the same tools that they've been using on Dell servers or DGXs. And that's, they really aren't changing anything. They just have more flexibility to scale up or reprovision their resources. So they might have to burst to the cloud less, but it doesn't interfere with anything from the really the PCIe bus up. So customers
while doing that, also, do they get to choose what % of the workload goes to cloud versus to you? Or
oh yeah, absolutely, yeah. They can still use whatever hybrid cloud tool they're using. Kind of like I mentioned earlier, I'm using Ansible a lot just to control everything. Mm-hmm. But I just maybe I'm a little crazy. I like explicit control of stuff when it comes to IT equipment. But yeah, they can do it however they're currently doing it, or there's no real.
Okay.
Change.
So a related question on that. Another thing is a lot of these companies because GPUs are quite expensive to buy and set it up in the whole 9 yards, they have a modeling software that they try to analyze the workload first to say that, you know what, this is a combination I want to allocate rather than you deciding it. They want to tell you some of this workload, even if it takes a little bit longer, I want to run it in a GPU combinational cloud, a CPU combinational cloud. Yes, it takes longer, but I would rather do that because I have a lot of them sitting around and everybody's asking for a GPU resource. Do you have a provision to help them out in such situations?
Yeah, with CPUs, today we don't have there's not a specific, it depends on what you're talking about. So if you're talking about like the root complex CPU of a server, today we don't pool CPU, the root complexes together and join them together.
You would think the memory stuff that Sumit was talking about, the Offtime Memory, where you could carve it up and assign it to a CPU, would be beneficial from CPU training or inferencing and that sort of stuff. Also, obviously, the storage stuff is something you can carve up and allocate on demand almost. So.
Yeah, no, absolutely. And to be honest with you, the reason we don't do CPU, we don't join CPUs and create, like mega compute servers, which is CPUs, is kind of goes back to that thing we talked about with NVLink, and I alluded to about that PLX, that like kind of core building block for our PCIe and actually most PCIe fabrics, and it's just. If you look at two CPUs, they've got 50 to 200 some gigabyte interconnect between them, and if you start putting a bunch of those together that don't have that speed, we kind of see that with the Rome process or the EPYC processors, where they took that route and they basically used PCIe Gen 4 with the XGMI interconnect, and it's kind of a known thing. If you got to do if you have to hop across that bridge, even between CPUs, you take a hit. So that's why we haven't really pursued that. And then we'd also be competing with AMD and Intel, who are like really good partners of ours, and we'll let them handle that CPU to CPU interconnect problem. Yeah. Now, I will say this, like with ARM processors, that's a little bit different of a story. So there are a lot of devices that are coming out that are basically, banks of ARM processors on PCIe devices that we do have customers that use.
Well, it seems like that's where the data center is heading. I mean, with all this talk of NVIDIA Grace and CXL and the ARM in the data center and composable infrastructure and everything, it seems like we're going to be seeing just racks of CPUs and racks of memory and racks of storage and racks of GPU and racks of FPGA and everything being composed dynamically.
Yeah, that's what I'd say we're hoping for, but also that's definitely like the trend that's happened, So we went from like mainframes to, regular x86 servers, so basically that mainframe disaggregated, right? And then we had more compute resources and memory resources than we needed there for a little while on the CPUs, and kind of those rack mount servers, and then virtualization popped up. Now you can disaggregate the operating systems and the applications on the same system, and now we're just kind of hitting this natural point where the technology has matured enough where it's the devices now, so and it coincides with what's going on in the deep learning and AI world, where there's a need for that, so.
And
so
Josiah,
yeah, go ahead.
There's something to say also is we're working on demoing CXL at Supercomputing 21 in November, which will be our first live event in like almost 2 years probably. But the idea there is we're going to disaggregate the DDR5 memory. It doesn't quite look like sticks of RAM, looks more like a U.2 drive, but that's our intention, is to demo that at Supercomputing. So pretty exciting stuff. And just to goes to show that, CXL Compute Link Interconnect is part of, PCIe Gen 5. It's real, so it's happening.
Right.